All right, welcome everyone. So in this video, I want to just give a very brief overview of what your task is for Python Lab number 2. So right now I have Python Lab 2 IPYNB, the interactive Python notebook, open using Google Collaboratory. So that's the interface that we are looking at here. So step one would be, so the instructions for the assignment are down here. So step one would be to save this document into your own Google Drive so that you can edit it. The permissions for this file are that you can view it only. So you won't be able to edit the file until you save it into your own Google Drive. So some preliminaries with Google Colab. First of all, just navigating around the document. There is a table of contents that you can open clicking this button over here. And this is useful if you want to kind of jump around to one particular part of the document. And you can see the questions in this assignment are down at the bottom. So I would definitely encourage you to jump in and out of the table of contents as you see fit. Another convenient way to navigate around the document is to expand and collapse different parts of the document. So for example, clicking this arrow next to Python Lab 2, which has the guided example and the instructions, will collapse the entire thing and then take you right down to the questions on the assignment. So if you ever see something like cells are hidden, that means that part of the document is collapsed and you can just hit this arrow to expand it. And so that's just for ease of displaying or hiding various parts of the document. So in this lab, we are going to solve systems of linear equations using some of the methods we did in Python Lab 1, doing row reduction, using the matrix reduced row echelon form function in SymPy, and we'll introduce another function in this one, the linalg solve function, which is in NumPy. And just be aware that that function has some limitations that we want to be careful about. And so after practicing these techniques, you'll apply these methods to solve a Leontief input-output economic model for Netherlands. So we'll be able to use more realistic data to solve more computational intensive problems because we've got Python to do some of the heavy lifting. So just to remind you, what you need to do is answer the questions at the very end of the document, save your work using the naming convention, your first name, your last name, Python 2, and then up into Python Lab 2, which is located in the in our Canvas website. So the goal of this assignment is that you can read through the guided example below, and that's going to give you all of the practice and all of the information that you'll need to complete the assignment. If you have some questions and after reading the guided example, you're not quite sure what to do, please just send me an email, come by office hours. I'm here to help you. So I realize the learning curve for working in Google Colab is going to be different for different people. So if you are having trouble, that's normal when you're learning new technology, but don't be afraid to get some help. So I will walk through the guided example in this video if it helps me to explain what's going on. And then at the end, you've got some problems to practice this. You may be fine just reading through this document on your own and not needing to listen to me. So just recall, first of all, that we're going to try and solve systems of linear equations. So up top, I have an example of a system that we might want to solve. So here's a system of 3 linear equations with 3 unknowns. And recall, if you want to see how this equation was typed using LaTeX, you can just double click on the text cell and you'll see the LaTeX code here. And so I've typeset this in a couple of different ways, just if you want to get some more practice working with the array environment in LaTeX. This assignment mainly is focusing on using Python to solve a system of linear equations. So from that system above, we can set up what I'll call matrix A, which is the coefficient matrix for that system. Matrix M is the augmented matrix for that system. Column vector B are the constants that were on the right side of each of the linear equations. And we've got our vector X, which is holding the variables X1, X2, and X3. So that linear equation that we had up here has an equivalent matrix equation down below, where A is the coefficient matrix and B are the constants on the right side. And so one way that we could solve this would be going through all of the details ourselves using row reduction. So I'm going to work with arrays. So that's why I'm going to import the NumPy library. And every time I call in a function from the NumPy library, I'm going to have a prefix of NP. So here I'm entering in the augmented matrix M for that system of linear equations. And you can follow the process below. I'm going to do row operations on this. So for example, I have a pivot over here in the 2 position. So let me eliminate the entries below that first pivot, the 4 and the -2, by doing some elementary row operations on the matrix. And so recall that when you're working in Python, Python indexes starting from 0, and we want to be aware of that. So if I want to replace row 2 in this matrix, row 2 in the matrix actually has an index of 1, since row 1 would be row 0 or index 0, row 2 is in excuse me, let me say that again. The first row of the matrix has index 0, the second row of the matrix has index 1, and the third row of the matrix has index 2. So just keep that in mind as you're doing your row operations. So these 2 row operations below, I'm going to do a replacement on row 2. So notice in my code, I have a comment that begins with the pound symbol, the hashtag, and I'm describing what the operation I'm going to do. And then I actually do the operation down here. Here, I'm going to do a second operation. So I'm going to eliminate this one to make this 0. And then I'm going to do a replacement on row 3 to make that 0. And then let me check my work before doing anything else. So that's what this print command does. So running this, I can see the output after this stage. And now keep in mind, when I go into this next text, or excuse me, this next code cell, the matrix M is now stored as the most recent output from the previous block. And now if I want to continue this process, I want my next pivot is in column 2. So let's make this entry below it equal to 0 by doing another replacement operation on row 3 that I've described here. And so now this row index 2, remember, is referring to actual row 3 in the matrix. And now I can check my operation after this stage. Great, I have a pivot in column 1, I have a pivot in column 2, I have a pivot in column 3. And then we can start to eliminate the entries above that pivot. That's what's going on in this cell with a couple of operations. Now I can go ahead and eliminate the entry above pivot 2 over here. We can check that. And finally, we need to do a couple of scaling operations on row 1 and row 2 so that those pivots are 1. And now we can see this matrix is in reduced row echelon form. And since we don't have any free variables, we have a unique solution. And so in the text box below, I coded up in using LaTeX the solution, right? So this is telling me that x1 is equal to 1, x2 is also equal to 1, and x3 is equal to 2. And that's what I've coded down here. And if you want to actually see what the LaTeX code is, we can double click on this cell. And this is how I coded the vector using the B matrix environment. That means put the matrix between brackets, square brackets. So that's one way of going about it, step by step by step. And that's really nice because we can practice our row operations that way. Recall last week, the last lab, we also talked about this matrix reduced row echelon form function built into the SymPy library. So if I want to use this function, I need to import SymPy. I need to do this once. If I want to use any functions in SymPy in any code blocks that come after this, I don't need to import SymPy again, but I do need to reference any of those functions with the prefix SymPy. And I need to redefine my matrix M, keep in mind, because we did a whole bunch of operations on matrix M in the previous example using the row operations. So I'm going to reset matrix M to the original augmented matrix. And you can see here, this is really nice. I don't need to do any of these operations. This function, matrix reduced row echelon form, will do it for us. And we can see over here, we have the same exact solution that we obtained ourselves going through Gaussian elimination, doing the row reduction ourselves. And when you use this SymPy matrix reduced row echelon form, we get a little tuple at the end. So here we first see the reduced row echelon form of the matrix, and then we get this little extra information over here. So this tuple is telling us the column indices for each column that has a pivot. So column index 0 has a pivot, and for us, that means column 1 of the matrix. This tells me that column 2 of the matrix has a pivot, and this tells me that column 3 of the matrix has a pivot. And sometimes you might not want to see that information. So for example, if I do something, if I add an option into the parentheses next to the reduced row echelon form part of this function, pivots equals false, that will do the same exact thing. It's just going to present the matrix in a nicer form as what we had up top. And I don't get the tuple there. The tuple is not all that useful, since for a relatively small matrix, we can kind of see where the pivots are ourselves. So just know there are options in a lot of these functions to customize things. Here's another example just to see what might happen if you have a matrix that has some free variables in it. So maybe this matrix is the augmented matrix of some really complicated looking system of equations. And you can see here I entered matrix M. I ran this function matrix reduced row echelon form on the new matrix M, and out below comes the reduced row echelon form. And here I can see that column 1 has a pivot, column 2 has a pivot, and column 5 has a pivot. That means where columns 3 and columns 4 don't have pivots. So those are free variables. So 3 and 4 are free variables. And down below, I go through, recall we've talked about different ways of representing solution sets. And so I go through how I could represent this solution set in vector form, as well as in parametric form down below. And all of the code for the LaTeX you can see behind the scenes when you double click on one of these text cells. So part of your assignment is going to be to also LaTeX up your solution. And then the last method, so this is new, we have not used this function, which is called linalg solve. So linalg solve we can use to solve the matrix equation AX equals B. So rather than look at the augmented matrix, which would include the constants on the right, we define matrix A as just the coefficients in front of each of our variables, x1, x2, and x3. So this is a 3x3 matrix, whereas the augmented matrix would be a 3x4 matrix. So we have the coefficients in one matrix, and then we have that last column B in its own separate column vector. So this function, linalg solve, is built into the NumPy library, and it has two inputs. So first we input the coefficient matrix, Then we input the constant vector b. So here I entered the corresponding coefficient matrix for that first system that we already solved. Here's the column vector of constants. And now I'm going to save the solution to this object X. So this command is going to solve the system, well, hopefully, and it's going to store it in X. So down below, if I actually want to see what the solution is, I need to use a print command to print that to the screen. So here is the function again, linealge solve. First, we enter the coefficient matrix, then we enter the constant, the vector of constants. And out comes the same solution that we got using row operations ourselves or using the matrix reduced row echelon form function in SymPy. So either way, they're giving us consistent results. If I want to use linealge solve to compare what we did with this larger system, right, that had a bunch of free variables in it, if I try and use linealge solve to solve this system, right, I get an error message down below. And the problem is linealge solve has a couple of limitations. The first limitation is that it can only be applied if the matrix of coefficients A is square matrix. So in other words, linealge solve can only be used to solve systems of linear equations where we have the same number of equations as we have variables in the equations. And if that is not the case, linealge solve will give you an error like we saw below. And that means you would probably want to use the matrix reduced row echelon form function in SymPy, because that works regardless of the size of the matrix. So that's one thing to keep in mind. And down below, I just have a little summary of each of these methods and what might be the pros and cons of them. It might be good for you to list your own pros and cons. You can edit this document as you like. But a second limitation that we did not see in this example, but we will see in future examples, is that this linealge solve only works when the system has a unique solution, when there aren't any free variables. So when we have a system that has some free variables, even if the matrix of coefficients is square, we're going to get some output that might be misleading. So if you want to avoid making any of those mistakes, that SymPy matrix reduced row echelon form function is super nice because we can use it in any situation, and it handles situations where we have free variables or when we don't have free variables. So down here, I just have a summary of some of the skills that hopefully you've practiced in this assignment. And after going through this guided example, hopefully you're now ready to answer the questions at the end of the document. So let me collapse this introduction. And now we can kind of look at what you're going to have to work on this assignment. So question 1 is asking you to solve this system of linear equations going through the step-by-step row reduction. And each time you're going to do an operation, I want you to explain what that operation is using a comment and then enter one line of code that does that operation. So question 1 is going to ask you to go through this step-by-step process. So I've imported NumPy as MP down here again, and I loaded the matrix M for you. So this is the augmented matrix. And I started the process. So here's our matrix. And for example, the very first thing you might want to do is make all of the entries below the first pivot 0. So in other words, I can replace row 2 in the matrix by taking row 2 and subtracting 2 times row 1. And that's what this line over here is doing. So when you're working on this problem, be sure you have a comment like this that explains what you're doing then a command that actually does it. And since the next step in this process is going to depend on what we get after this first step, it might be useful to actually print your output to the screen. I'll do that one here, because now I know what to do next. It's useful to see this matrix because now I know I've got the next pivot over here, and I want to eliminate this value below it. I want that to be 0. And that might not be evident unless you print this output to the screen. So I've added an additional block of code here to do the next operation, and I've indicated that operation for you. So what I'd like you to do next is replace these question marks with a line of code that's actually gonna do this operation over here. And then print that output to the screen again. And now you're in control of what you would like to do next. And so down here, you can enter a comment and say, describe the operation as I've been doing up top. And then you'll enter a line that actually does that operation below. And if you want to do one operation at a time and print the output before you do the next one, that's fine. Might be a good way of doing it. If you are comfortable doing all of the operations in one block of code at once, that's fine too. Just keep in mind, if you want to add an additional block of code, then you can just hit this add code button right here, and that will plop down a new bit of code. So if you printed out some output over here, you can see that output, add a new block of code, and then do your next operation down below. So that's probably going to be the most involved question because you're going to have to go through that step by step. Question 2 is going to have you check your work from the first question using this really nice matrix RREF function. So it's the same system of equations. I've teched in the various components of this system, and I started a block of code for Python where I've defined the augmented matrix, the coefficient matrix, and the vector of constants. And all you need to do in this case is replace these question marks with an appropriate object. Question 3 is pretty similar. Again, we're going to save some time by using this nice built-in function in NumPy. So I've entered in M and A and P. And all you need to do is figure out what goes in the question marks over here to get the solution. So you should find in questions 1, 2, and 3, you have the same solution set. And question 4 is asking you to LaTeX that solution set. So if you want to LaTeX, enter LaTeX, that means you're going to need to double click on this text box. And then in place of these question marks, you're probably going to want to use begin the matrix, and then you would enter your values each time you end a column. So let's say my solution is 5, 6, 7, and B matrix, and that would enter, oh, there we go. And that would enter my solution that looks like 5, 6, 7. So you'll have a different solution probably, but whatever that solution is, that's what you would want to enter in this place. I'll put the question marks back. So the question marks are a placeholder. Question 5 is going to deal with looking at an input-output table for the economy of Netherlands. And so you don't need to do any of this work, but if you're curious about where the matrix comes from that you'll be working with, here's kind of the background of the problem. And here's the important part of the problem, which is the exchange table. And so we're going to want to find the equilibrium for this economy, which leads to a bunch of system of equations down below here. Again, this is not something you're responsible of doing, but if you're curious about where the system of equations comes from that you'll be working with, that's what's being described in this part of the document. So to find the equilibrium for the Netherlands economy, it comes down to solving a system of 6 equations with 6 unknowns here. And if you don't care about the application, you can just think about what's the math problem down below. We have this augmented matrix M, and I would like to solve the corresponding system of linear equations to this augmented matrix. So down below, go ahead and try and solve this system. My recommendation is to use the SymPy matrix reduced row echelon form. And once you get that solution, you should see that there's a free variable involved, namely the price in the service sector. So then, similar to what you did in the previous problem, I'd like you to come into this text code. We can double click on it and then replace these question marks with the corresponding solution that you found in the previous block of R code. And then very last thing to do, we know the output from the service sector is given to us as 150,099 million euros. So from this, if we know what the value of the free variable is, you should be able to pull off some information from the previous solution to figure out what the target outputs would be for the other sectors: agricultural, mining, manufacturing, utilities, and construction. So this block of code is going to print to the screen. You won't need to edit any of these lines over here. The equilibrium for the economy in the Netherlands. The only thing you'll need to do in this block of code is replace each of these question marks. Okay, well, happy coding on this problem. And if you have any questions on this lab, please don't hesitate to reach out with your questions.